Pamela.
You're loud.
That's just.
Hi.
I am loud, and also you probably have your microphone set really loud.
I think it's the headphones are probably more an issue right now.
Headphones. How's it going?
It's going okay, other than gravity is defeating my microphone, but that's a personal problem.
Gravity always lets you down.
Yeah, it sadly does. It sadly does. How are things there?
Good. Well, I finished an epic journey driving across your country last week from Louisiana to Vancouver Island, and it was fun. It wasn't fun. It was just big. It was a grueling death march across the United States. But here we are, back on Vancouver Island, where it's foggy. So, and now I have dogs. So you won't be the only one who'll have a dog go click clack click clack through your living room or through your office. I will now have the same thing happen. So we can get it synchronized.
Very cool. And I just learned that they now auto start Hangouts. I had this hidden window somewhere on my two screens, and there's apparently about a 5-second delay between when you say something and when it actually goes live on YouTube.
Yeah, I did little. That's right. You are hearing me from the future.
I am. It's very exciting. I like to be in the future.
So let's see. So what do we got? So today we're going to do episode 369, the Fizeau Experiment. Fizeau? Yeah.
I have no idea.
Yeah. Fizeau.
I can explain the experiment. Can't pronounce the name.
Okay. And so this is our ongoing series on cool experiments in physics and astronomy. So we always talk about how we know what we know, and this is it. This is exactly how we learned what we know, which is just a wonderful way to do this. So again, thanks to what was her name again? Rachel? Anyway, who recommended this series. So we're pushing through. It's awesome. Although someone else, we got a few more recommendations on series as well, which I think is great. One little piece of housekeeping. Well, I'll mention it in the actual show itself, so don't worry about it. But we're going to stick around to the end of the show. As always, we'll do the record for about 30 minutes, and then stick around after, and we will answer your questions about space and astronomy, as well as questions that have been submitted to us by email, which we get lots of questions, and so we'll be tackling that there. Are you ready to record?
I think so.
Okay, let's do it.
I am pressing record. It's recording. It's using the right mic in mono. Yep. Hello, Preston.
My levels are really low.
We need to start over?
No, I don't know why it's so low.
Okay, I'm stopping. Go into System Preferences and jack it up if you're on a Mac, and if you're on Windows, I am of no help.
Yeah, if I'm on Windows, you don't care. Testing. No, I know you do.
I just don't know how to fix it if you're on Windows.
Yeah, it's really low. Hold on.
I abandoned Windows when XP was no longer a thing.
Apologize, everybody.
While he plays, I'm going to say hello to people. We have Helge Borchang. I want your name. Okay. Thank you. Peter Waldman, Tony Lynch, Guido Bibra, Arn Milne, who's asking a question, I think? Yes. Nancy Graziano, Dan Bryce. It looks like the whole crew is here. You guys are awesome. Nancy's already asking, what kind of dogs? It looks like they're mutts, the best kind.
One is a English Bull Terrier. And the other one is a mutt, yeah, kind of half Basset Hound and half Boxer.
That's kind of hilarious in all kinds of ways.
It is, yeah. She's a very hilarious dog, but she's good. Okay, I'm going to stop this and start the recording again. Let's see what happens.
Okay. I'm pressing record again. I'm again saying hello to Preston and hoping that Fraser's audio...
Testing. Yeah, that's way better. Okay, good. All right. Let's get cracking. Hey, Preston. Here we go. Astronomy Cast, episode 369, the Fizeau Experiment. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Doing great. We've got a bit of an announcement to make today, right?
I think we probably have more than one, but the big one is that we are announcing the CosmoQuest Hangout-a-thon will occur for 36 straight hours starting on,
Oh, no, that's gonna be
starting
fun.
9 a.m. Saturday, 9 a.m. Central Time, Saturday, April 25th, going into April 26th. And I'm going to be putting out the announcements. Well, I'm halfway done with the graphic, so when I'm done with the graphic and have everything posted on Google, it's going up. And this year, funding, yes, priority. Actually, the only reason we exist right now in the face of everything going on with NASA is because of your funding. We're in the middle of putting in a frighteningly large NASA grant that if we get it, we'll get it in September. If we don't get it, I cry a whole lot because the next time there's a proposal is 5 years from now. So we need your help to make it till September, and there's no one else out there to help us. So donate now, donate tomorrow, donate often, but also do the science, because if you don't do the science, we shouldn't exist. And so for the Hangout-a-thon, we're going to have lots of cool prizes for people who participate doing science throughout the Hangout-a-thon. So come in,
Okay.
help us explore, and help us survive.
Perfect. I can't wait.
Yes, you can, but you're faking it well.
No, you're a trooper. Every time you do these, it's crazy to see how much energy you put into it. And any support I can give, I'm happy to help out. And all of our friends will pitch in too, I'm sure. I speak for everyone when I say we'll all be pitching in. The other thing, just a quick announcement or just a quick mention, is that a lot of you have your questions about space and astronomy, and as you may know, we stick around half an hour after every recording of Astronomy Cast when we do it live, and we answer your questions. So all of the questions that get sent to us by email, we throw them into a folder, and I will be submitting some of those to Pamela every week as well. So if you want to hear the answer to your question, those are available on the YouTube video. And we'll probably start making things more available in other kinds of feeds. I'd love to hear your recommendations. Do you want like the whole show, just the raw audio of the whole show? Do you just want Astronomy Cast? Do you just want the questions part? You know, or are you happy to just go to YouTube and watch the video there? Anyway, so let us know how you'd like to be able to, how you access the Astronomy Cast feed, and we'll do what we
You're
can.
going to kill me. My audio stopped 25 seconds in.
No!
Yes. We get to
Okay.
make the sausage again.
Hey, everybody, you get to watch this happen again. All right, I'm going to stop this.
I must have accidentally touched something.
Okay, I've deleted my recording. So let me know when you're ready.
I've pressed record. This is attempt 3, and this time it's my fault that we're starting over. Hello, a third time, and this is the first time you're hearing it, Preston.
Okay. Astronomy Cast, episode 369, the Fizeau Experiment. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we'll help you understand not only what we know, but how we know what we know. My name is Fraser Cain. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville, and the director of CosmoQuest. Hey, Pamela, how you doing?
I'm doing well. How are you doing, Fraser?
Doing great. We've got a couple of announcements to make today, so why don't you go first?
Well, I think the biggest one is we have coming on April 25, 26, the 36-hour CosmoQuest Hangout-a-thon. So far, the only reason we're still going in the face of NASA cuts is because of awesome people out there donating to keep our programs going. We are in the process of writing a giant NASA grant, and if we get it, we will have the money in September. If we don't get it, I will personally cry a lot because this is a once in every 5-year opportunity. But we have to still be going in September, and we need your help to do it. This year, unlike past years, we're going to ask people to show up and not just give money, but also donate their time to clicking on pictures of worlds and helping us map them out, because if we're not producing science, we might as well not exist. So come do science, come hang out, watch me lose my mind over 36 straight hours. Fraser will be joining me, and let's map other worlds and raise money to keep the science going in the face of, well, politically driven budget cuts.
All right. And then the second thing, just to let you know, if you didn't know, we record Astronomy Cast actually as a live Google Plus Hangout. We take an hour to do the whole show. The first half an hour, we record the show that you're listening to right now, and then we stick around for another half hour and answer questions live from the audience about space and astronomy. And in addition, I will be sort of asking for you the questions that we get by email. So if you have a question about space and astronomy, just go ahead and email us, info@astronomycast.com. But you won't hear the answer unless you come and watch the full-length video. So sorry, but I think we're going to want to experiment a bit and maybe make some of the audio available in other methods. So we'll probably either release full audio in a different feed or release the question show separate in the feed. We'll figure this out. But let us know how you consume Astronomy Cast so that we can make this stuff available to you. All right, let's get rolling. So light is tricky stuff, and it took scientists hundreds of years to puzzle out what it is. But they poked and prodded at it with many clever experiments to try and measure it. They poked it and prodded it with many clever experiments to try and measure its speed, motion, and interaction with the rest of the universe. For example, the Fizeau Experiment, which ran light through moving water to see if that caused a difference. All right, Pamela, set the scene for us. When did this experiment happen?
This was in 1851. This fell just a couple of years after Fizeau had successfully become the first person to accurately measure the speed of light, and was part of the process of trying to figure out how is it that light is affected, altered, slowed as it goes from one medium to another, and in particular, how does the effect of that medium moving and, well, our own motion through the, at the time, supposed ether affect everything as well?
Okay, so Fizeau had fairly accurately determined the speed of light, and I guess that was a shock because people weren't even sure that light had a speed, right? That's kind of a weird thing to think about, but I guess they knew that sound had a speed, and so.
And we had some early kind of bad estimates of the speed of light that were based on things as simple as using orbital mechanics equations. Folks have been able to figure out when you should be able to see various moons emerging from behind Jupiter. And it was found that if you were nearest to Jupiter on one side of the sun, the amount of time that it would take to see Io emerge from the far side of Jupiter was a different amount of time than if you were on the other side of the sun further away. And this difference in when you finally got to see the information arrive at Earth gave our first initial understanding of what order of magnitude the speed of light might be. But that's really all we had at that point was wow, that's a big number. You can't do this reasonably. But then Fizeau came along.
That's a pretty elegant experiment to think about it. Like, it's the kind of thing that as soon as you had a telescope, you could probably start working. You could probably come up with that experiment and do your timings once you knew the positions of the moons. Okay, so Fizeau did his experiment, and what was his experiment for actually measure the speed of light?
He took a cogwheel that had 720 very precisely made notches up and slots down that were the exact same size going all the way around it. And he set up an optical experiment that was actually 8 kilometers across. Outside of Paris on 2 different hills, he set up systems where on one side he took light, focused it through a lens so that it came down to a point. That point where it came into focus was just as it was sliding through where the cogs would be. Then it came through to another lens that collimated it to send a beam of light across Paris. Then 8 kilometers away, that beam of light got intercepted, focused back down onto a mirror, reflected off of that mirror, and started its way back across the city. So now you're looking at a significant difference. But they knew what that distance was. And the neat thing was, if you're looking at the light and you start out with the cog not moving, the light will clearly go through, reflect, come back, you see light. If you start the cog spinning, you will see light, not light, light, not light, as the cogs block out the light that's coming towards you. Now, as you spin it faster, you eventually reach a point where the light takes off, comes back, and instead of coming back through that same slot in the cog, it instead hits the tab. Now, if you know how fast the cog is turning, then you know how wide, and you know how wide each of those slots are, you can calculate the amount of time it takes for that last bit of light to leave and come back, and this gives you a within 2% measurement of the speed of light.
That is really cool. So I can imagine, right, that it's all in the timing, right? That if that the slots have moved enough that the light, instead of being able to come back through that slot, now bonks into the block, and then you don't get the light. And so I guess you spin up the wheel to the point that you no longer see that light, and then boom, you've measured your speed of light. That's such an amazing experiment, and they did that. It's so brilliant.
And it's so simple at a certain point. Not spinning constant light, slowly spinning, light, not light, light, not light, spinning fast enough the light never gets back.
And if you had like a green laser,
you can replicate this. And what's awesome, they did this in 1849.
Yeah.
No,
how did they do that without a laser? Right? Like, how did they make a light that could be focused to go 8 miles, right?
It was 8 kilometers, 5-ish miles.
Each way.
Yeah. And it was all about using a bright enough light, collimated so that it just like a laser is collimated. So you can do that with lenses. So they took regular old light, collimated it with hand-ground lenses. No machines were harmed in the making of this experiment. And everything was mechanical. That's the amazingness of this. This was in the days of hand-wound clocks, hand-wound gears, springs, levers. I mean, they weren't hand-winding the gear that they were using for this experiment. Clearly, that would have been super imprecise. But it was still kind of, like I said, no machines were harmed in the making of this experiment.
And the number, as you said, the number that they got was within 2% of our modern understanding of the speed of light.
And if you give this experiment to a group of students today, they're going to be like, there's too much light pollution, this is too hard, how do we measure the distances? And the thing is, yeah, he didn't have as much light pollution, but he sure had a lot of coal dust. He figured this out. He did it accurately across a major metropolis.
So this is how. So I guess the first way, back to how we know what we know, right? You want to measure the speed of light, measure the time it takes for Jupiter's moons to appear behind the planet. Boom, you've got an experiment you can do. The second one was developed by Fizeau, but he continued on with his experiments, right? It's a matter of like what effect is it going to have moving through a medium. So I guess what was the thinking at the time about what might happen with light as it moved through these various mediums?
So it was messy. We knew going back to Newton and even earlier, just when people started making glasses, that when light hits different medium, its speed changes, and this is what causes the bending that we see at a certain level. And as early as 1807, Thomas Young started talking about what he coined the term the refractive index of a medium. Earlier, folks like Newton had used ratios, and it was just much more cumbersome to deal with. And he's like, no, we're going to talk about this in terms of refractive index, and this compares everything to vacuum. What is the amount that the speed of light gets changed when an object enters a median. So if you have your normal speed of light, you take the phase velocity and multiply it by this index of refraction, and that new number is equal to the speed of light.
Okay, and so I guess back to my question, what were they sort of expecting was going to happen?
So
what do they not understand about
a
light?
given medium, so if you have water that's not moving, you know that when you send the light beam into that non-moving water, the speed of light is going to slow as the light enters that water, and you can actually measure this through different interference experiments. So send a beam of light through water, send a beam of light through vacuum, recombine them, look at the interference fringes. This tells you the difference in the distance the two different beams traveled, which is another way of saying the different rate at which they traveled. Now, what happens if that median is moving, though? So the idea was, let's say that you're trying to walk forward in an airport, and for whatever reason you step on the moving walkway that's going in the wrong direction. You're essentially going to double, triple the distance you have to walk because you're going against the movement of the moving walkway. So your velocity relative to people not on the moving walkway is the rate at which you're walking relative to the walkway plus the walkway's motion. So far, are you with me?
Yeah, and I'm imagining sort of another model of that, which is like, imagine that you're hearing a sound from while you're in the middle of a hurricane.
Ignore sound. Yeah.
Okay. No, but if you're hearing sound and you're in a hurricane, right, and the wind is blowing towards you, is that going to have any impact on the wavelengths of the sound?
So we're not talking about wavelengths right now.
I understand.
We're only talking about velocities.
Yes.
And they were doing all of this with white light, so they weren't paying attention to the Doppler shifting either. We're simply looking at the velocity, not the change in color right now.
Right.
So,
okay. But I guess the point though is that if the medium is moving towards you, then in theory the velocity of the light should speed up. And if the medium is moving away from you, then the velocity you should see the velocity slow down. And if the medium is moving sideways, then you should see no real change in the velocity.
Exactly. Okay. And you're moving walkways.
Perfectly rational thing to expect.
So they went and they did the experiment. So you have Fizeau. And this is what's called either the, capital T, the Fizeau experiment. And he did hundreds of experiments. So that's kind of unfair to the poor guy. He did a lot of work.
So Fizeau?
Yes.
Yeah.
Again, can't pronounce his name. Or it's called his water experiment. That's how Einstein often referred to it. So what he did was he took a beam of light and a beam splitter. So he took the one beam, split it into two beams. One of those two beams he sent through a tube of water where the water was rushing in the direction the light was moving, reflected it off of a mirror on the other side rather, and it came back through another tube that had the water rushing toward the observer. Now with another beam of light he went the exact opposite path. So the opposite path, you're constantly going the opposite direction of the water. And this was an experiment that had to be done extraordinarily quickly because he essentially had a water reserve on both sides, let gravity move the water through the system. And once he was out of water, he was out of water. And in order to keep constant velocity of the water, you have to have a very shallow, very large surface area container that you're draining out of so that you don't have to deal with the height of the water changing the velocity it's coming out very much. It's basically a pain to do this. Today we have things like water pumps that he just didn't have. He had gravity. So did the experiment, did it very quickly, and what you would expect is you have light going with the current and against the current through these two different paths. It gets recombined. You look at the interference fringes. You look for the difference in how long the light was traveling. And what he found was the rate of the water absolutely had nothing to do with the experiment.
What?
Yeah.
But this is unexpected. This is not what you were expecting. We just need to know what the number is.
And what's worse is there was a change. It just had nothing to do with the rate of the water.
So he actually did detect a minor dragging effect by the water, right?
Yeah. So it's unfair to say that it had nothing to do with the rate of the water. It just wasn't linearly proportional to the rate of the water. So if the water's not moving, the measured velocity is equal to the speed of light divided by the index of refraction. If you work through the maths of what he was expecting it to be speed of light divided by index of refraction plus the velocity of the water. It was not plus the velocity of the water. It was plus the velocity of water times this little tiny, tiny number that was 1 minus 1 over the index of refraction squared. Really tiny, tiny effect that was annoyingly directly related to a physical quantity. So this is one of those times where you get a result and you're like, what the hell? I got a result. It has nothing to do with what I was expecting. What equation actually fits my data? And this actually had some backing in it. There'd been other experiments that found that things were proportional to this 1 minus 1 over the index of refraction squared. And this was considered to be an incomplete linking of what was going on to the ether. And so you're in this situation kind of like trying to understand the motion of the planets if you're Kepler. You know they're moving. You're not sure why they're moving. You have ellipses. Ellipses work. You're not sure why ellipses work, but they work, so you have 3 laws named after you.
Right.
In this case, we have what has gone on because of the interference work that was done to be called the Fresnel drag coefficient, which is the 1 minus 1 over index of refraction squared. And it is exactly what our fair French-named fellow found in his water forcing experiment.
So explain this, Einstein.
Sure, he did. So up through 1904, people kept doing experiments going, what the, insert expletives in appropriate foreign language, kept doing this over, replicating with different media, increasing the accuracy. Michelson Morley got involved. They had systems that were able to pump the water for longer durations and apparatus that were much less likely to flex. Increased accuracy was found, we know this is what's happening was found, and increased confusion as to why. We had in 1895 Henrik Lorenz, who was really the person doing the moral equivalent of Kepler in this particular area of science, figured out how to explain all of this using his contraction in the direction of motion equation. So here we're looking at Lorenz contraction, accurately explains what's going on.
Sorry, you just glossed over Lorenz contractions. Can you just give a quick explanation of what that is? The fact that things change in shape the faster they're moving.
Oh, they don't change in shape as
From
much
your
as
perspective,
they get distorted.
They get distorted.
So along the direction of motion, things are found to contract. So this means that a very fast-running pole vaulter can shrink the length of his pole if he runs fast enough, which might make it hard to get over the jump, but makes it easier to fit into a barn if that's what you're trying to do, which is what you're always trying to do in your physics homework sets.
How fast must the pole vaulter be running to be able to fit the pole vault through the barn?
Usually it's some fraction of the speed of light, depending on the size of the barn.
But a spaceship, let's just go back to the happy spaceship that we all understand. As the spaceship is moving towards you at the speed of light, or closing in on the speed of light, its length contracts from your perspective.
Only along the distance of travel. So this means that if you want to be very skinny, stand very tall and upright, perpendicular to the direction of motion. If you want to be very short, lie down on your side and your girth won't change, but you will suddenly be a shorter human.
Right. Okay. All right. And this is not, and you as the spaceship traveling
have no awareness.
No, but you see the Earth, for example, changing in its shape, right? Because it's all relative.
It's all relative. It's just messy.
Yeah.
But
and then, of course, you increase in mass, and can you turn into a black hole? We don't know. Anyway.
You can't. I finally got the answer to that, but that's a different show. We'll come back to that as a different show.
Awesome. Okay, great. So the point being that Fresnel thought that it was the interference, Fresnel thought it was the movement through the ether that was explaining this, and Lorenz came along and said, no, it turns out...
No, Lorenz didn't get rid of the ether. He just added an extra term.
Right, but he was starting to set the groundwork for what Einstein would then later be able to use.
So we're at the point where people are like, okay, if there's ether, we're not really attached to it all that well. It's not something that's creating a lot of dragging. Perhaps it builds up with larger amounts inside the prism than outside of the prism. All sorts of things were factored in. Heinrich Lorenz started trying to explain what was being seen as saying that instead of being attached to the ether, perhaps what we're seeing is contraction due to the direction of motion. So he didn't get rid of the ether, he simply found new mathematical explanations for what was going on that didn't require the ether. But all of this sort of set up the stage for Einstein to come along and working completely autonomous of Lorenz. This is the awesome thing, is Einstein didn't actually know about the Lorenz contraction according to some of the histories. He saw things like the experiment we're discussing and went, oh, this can be described by looking at how time is seen to actually change such that the speed of light is constant for everyone. And this change in the perceived speed of light is actually causing this contraction that, of course, was the exact same equation Lorenz had already come up with in 1895. And so in 1905, when Einstein published, suddenly we had a new context that was explaining from first principles, not from, we have this experiment and these numbers seem to line up with this equation, but rather from first principles what was going on.
So that's one of the big, I guess, this was the thing that Einstein was really looking to figure out. I mean, he saw the experiment, saw how everyone was trying to wrap their heads around it, and he thought in a completely unique way to explain what was going on. But he clearly was standing on the shoulders of giants. I mean, it's back to that statement that the Newton always makes, right? That made was that, it's not like Einstein just sat there and thought about the universe and then came up with his relativity. He saw and knew the challenges that the other physicists and experimenters were struggling with, saw what the outcomes of their experiments were, but then made this really creative leap to figure out what might be the underlying physics behind what we see.
And I love how this shows that scientists will completely throw out everything they thought they know. Because we went from this idea that waves require a medium to travel through, therefore let's invent the ether, to in 1810, Argo realized, well, it actually doesn't couple completely. We have this weird factor of the index of refraction, so let's call it partial ether dragging. But that didn't seem to work. So Lorenz tried to find ways to explain it with math based on what was going on, came up with the Lorenz contraction. You have our fair French fellow whose name I can't pronounce, who measured the speed of light and then looked to see how it was altered by moving mediums now that he had an accurate measurement, and found we're back to the partial frame dragging. This still isn't working correctly, to Einstein stepping forward and saying, wait, I've got some physics that will back all of this up. Now we have a more complete picture. And it's always more complete. It's never complete. It's just more complete.
I mean, I always think about these kinds of experiments, and you see, like, if you read the history of this experiment, and you see all of the, you just gave the synopsis of it, but all of the experiments and all of the theories and all of the math that everyone done, they've flipped back and forth and sort of narrowing down the options. We can now look back with history and go, well, obviously it was relativity, duh, but we're living through a bunch of these right now. Right? What is the nature of dark matter? What is the nature of dark energy? We don't know. We can only detect it. And as they ramp up experiments in the Large Hadron Collider and discount various theories and give further evidence to other theories, we start to move towards a more thorough understanding of what is the underlying process here. But it is still this, it is discovery at the very edge of understanding.
And it's really amazing how similar dark matter feels to the tracking down of the ether, just going in the opposite direction. Because you see the press releases coming out from various theorists along the lines of, we've figured out the excess heat in the Earth may be due to asymmetries and how dark matter and anti-dark matter particles interact. We are starting to figure out discrepancies in solar radiation that we hadn't been able to figure out before, as potentially explained by densities of dark matter inside the sun. Still not sure how I feel about that one. But there's all of these different things where now every place we have a discrepancy between theory and observation, people are like, wait, we have new tools. Let's take these new things that we know exist. We know dark matter is a thing. We see it through its gravity. Let's take these new things that we know about and try and sort out what role they play.
It's got to be tough when you're an experimenter and you've got maybe it's not a completely null result, but you've got a much different result than you were expecting, but you can't explain it. And then you can really see how useful it is and how amazing it is to have these various researchers talking to each other. They were sending each other letters, they were visiting one another, and bringing each other up to date on their experiments, and kind of going, well, I got this thing and I don't know what it means, and like I've been working on this, these kinds of experiments over here, and maybe what I'm detecting over here has something to do with what you're doing over there. There's so much of that cross-pollination. And now the internet has really even made that faster.
And that's actually something that really fascinates me, because you have all of these amazingly thoughtful, long letters sent between scientists that would sometimes take weeks to get from one place to another. And now we're dashing off half-hearted emails at every minor consideration. And you have to wonder if we might all just benefit from sitting down and being thoughtful with a 2-week delay now and then. Science is done so differently today. It's interesting to contemplate, and that's social sciences for you, how we've changed how science is thought about by changing how we communicate with one another.
Very cool. Well, we got another experiment next week, so stay tuned. Thanks, Pamela.
Thank you.
All right, save.
There are so many reasons I don't have my husband's last name that I demonstrated in today's failure to pronounce anything episode. I can't pronounce French. I don't know what it is. My brain just gives up.
So EAU.
I'm sorry, France.
EAU, right, is French for water. Oh, EAU. Oh, so I would assume it's Fizeau. Is water. Okay, I'm gonna export. Come on, save. Cool. Okay. And now I'm going to upload.
I'm setting up the Hangout-a-thon to see if I can get the donation link going live to give to our current audience so that they can share it out. Note, I'm asking you to share. I love that you're here. I'm not begging you for money. I'm begging you to share links.
Okay, I'm uploading. All right, let's take a look at some of the questions we got, and then we'll also handle some of the questions we got from email. So, cool. Arn Milne asks, what is the ratio of star to planet light for the JWST? The visible light, I understand it's something like 1,000,000 to 1. Often use the illustration as like trying to see a firefly next to a searchlight. So I guess the question is that how much less bright are planets in the infrared than their stars? Because
it depends on the star.
And it depends on the planet.
Really big planet next to really small star, you're starting to get to the point that it's fairly easy to see the planet.
But in infrared is better than visible light. Right?
Yeah, no, I'm talking in infrared. It maintains its firefly characteristics in the optical.
Right. So the point being that the James Webb Space Telescope, in theory, is all of these infrared telescopes are a much better gadget for finding planets than visible optical light. So lucky that the most powerful space telescope ever built happens to also be a very powerful infrared telescope. Yeah. And it wasn't a coincidence. Infrared is just good for all kinds of things.
Yeah, JWST is going to be answering everything from how did planets form to how did the universe form.
Right.
Nothing too hard in there.
No. What's at the heart of the Milky Way? How did planets form? Where are all the asteroids? Goes on and on.
I think LSST is going to get at that one first, though.
True, but it will definitely be able to observe and find faint objects in the infrared. Cavendish. So Steve Chisnell says, what about the Cavendish experiment? Did you put that on the list?
Yeah, it's on the list.
It's on the list. So Fred Miller asks, how did he make a disk with the slots precise enough? And I guess that's a good point. Very carefully?
Pretty much. I mean,
Fizeau,
I have to admit I don't know the details of how he did it, but I mean, even today, a lot of the most carefully made stuff is made by hand using templates.
Yeah, it's funny. I mean, these old experimenters were also really great machinists, and they were like the Mythbusters. They could build this stuff very carefully and then be able to run their experiments. They had to. It's only sort of in more modern times that the experimenters, the people who build and run the telescopes, build and run the various instruments are different from the scientists who are actually running the experiments. They used to have assistants who would help them, especially if they had someone who was quite crafty and helped build things. But quite cool.
Or in the case of the Herschels, quite bratty and drove you to do excellence.
Bill Troutman wants to know, does the bear on the shelf behind Pamela have a name?
It doesn't really. It's sort of like, so that teddy bear was a gift that I got in college that has the unique memory of I got it by someone who pushed me over on the ice while ice skating, who felt bad because I'd hurt my wrist, and then he put the bear up on a shelf where the wrist that he had the little fake bandage on, as it promptly got set on fire by a candle. And it's sort of my bad luck bear. It absorbs all the bad luck. And the hat it's wearing is one of P.G. Holyfield's hats that he was a dear friend, and his hat sits there as a friendly reminder. Right. So my bad luck absorbing P.G. Holyfield hat wearing teddy bear.
Fred Miller asks, I'm reading A Universe from Nothing, written by Lawrence Krauss, and he keeps referring to the universe as flat. Is he saying that the universe is coin-shaped? So we have an episode of Astronomy Cast. It's in the first 100. I think it's in the 70s, which is what shape is the universe?
Yeah.
And we explained that the universe is flat. But can you give the short version of what that means, that the universe is flat?
short version is if you have two light beams and you shoot them out, ignoring anything that gravity might do to them, if they're allowed to keep traveling, they will remain parallel to one another. If our universe was saddle-shaped, those light beams would migrate apart over time, and if it was a closed spherical universe, they'd merge together just like they do at the North and South Poles here on Earth.
Right, and so, if you're at the North Pole of the Earth and you shoot two laser beams that follow the path of the Earth, they will separate out until they reach the equator, and then they'll come back together. So that tells us, that the Earth is round. So it's spherical, and so scientists have actually done this experiment in the universe and tried shooting laser beams, and they're trying to see, of course, looking at the cosmic microwave background radiation in some way, and determine that the universe is flat. But flat doesn't mean flat like a coin. It means that it has a topology where you can have this, and there's a couple of kinds. And in the episode, of course, we did that the universe is a big donut. But you can imagine some other topologies at work as well. One example would be, say, a 20-sided die, a polyhedron. So you take two beams, you run them along a face on a polyhedron, and then they'll wrap down one facet, and they'll move along that one, and they'll remain parallel. And there's a bunch of topologies of the universe that can follow, that will still allow for light beams to remain parallel. So that just sort of means that it's flat. It's not a sphere. That's all.
And what's kind of awesome is we've only just figured out this geometry. This is thanks to WMAP, thanks more recently to Planck confirming those results. And so just knowing the geometry of the universe, we didn't know that when I was an undergrad.
So cool. All right, let me see. Fred Miller asks, is dark matter, dark energy ether?
No.
No.
No. Sorry.
Okay, so now I'm going to tackle a couple questions we got by email. So this one comes from Peter, and he says, hi guys, I wonder why we don't get video of launches with sound effects. This has always inspired me. So
what do you want with sound effects? It's
sound effects, yeah.
Loud. It's
already very loud. Yeah, so rockets, especially the space shuttle, like the space shuttle launching is one of the loudest sounds ever heard on Earth. Like, louder sounds are volcanoes going off and atomic bombs. But apart from that, the space shuttle, in terms of raw decibels, will destroy your hearing if you're too close. Easily, and even if you're not too close. And you've been at a space shuttle launch, right?
Yeah, it's really kind of awesome. You're just so far away that the shuttle looks like this small thing, like a Barbie toy on the horizon, and when it takes off, you feel it in your chest, and animals freak out for miles.
I guess once they get into space and then it's all silent, it would be cool to have some sound effects. So maybe someone should come with like some kind of
that's sad.
Some kind of, people could be like coconuts, banging coconuts together while the astronauts are walking around on the moon, or things like that. No, all right.
No. I'm like Firefly got it right. Space
with no sound.
is silent.
This comes from Barry Smith, and he just links to the Big Bang deflated universe may have had no beginning. So have you been following this at all, Pamela, in the last couple of weeks? Apparently, there's no Big Bang. So
I won't believe that.
Yeah, so a bunch of you actually asked us about this. So there's a new model of the universe, the Big Bang, origin of the universe, and that maybe there was no Big Bang. And actually, I'm going to direct you to Brian Koberline for this one. He wrote a great takedown of this. And I think that, what Brian was saying, and we've dealt with this a lot, is this idea of the clickbait. There's this idea of
Yeah, exactly.
somebody comes up with just like a model of the universe, and this is back to that idea, right? Like, what if there's dark energy being, is somehow causing the amount of heat coming out of the sun to be different than what we would be expecting, and maybe that's dark matter. The person just writes a paper and goes, hey, everybody, if you ever have the time and you want to run this experiment, here's something to maybe look for, maybe. And that somehow, the public relations person at that university picks up that question and says, oh, well, then you're saying that, there's dark matter in the sun. And, or in this case, the Big Bang never happened and we lived in an eternal universe. This is going to happen all the time. And in many cases, it's not even what the researcher was saying. And yet the public relations person just has to, build some clickbait for it. So.
And sadly, the kinds of things that we as university professors have to report is how many times we're asked to give public talks, how many papers result from what we do, and sometimes how many news articles actually kind of counts. And yeah. Funders definitely like it when you have more news articles. So it's tough as the press, and so you look at a lot of the... It's tough as the scientists.
Well, it's not my problem. I'm the press. But, it's tough. Both. But you see, that if you haven't been reporting on this stuff or had the opportunity to spend 369 episodes talking to a PhD astronomer to beat out every single one of your instincts about chasing after these stories like a dog going after a squirrel, which I would, to build that level of skepticism and to say, wait a minute, and then to get more quotes and to get more understanding, to put things in context is really tough. When especially there's no science reporting beats on a lot of large newspapers, a lot of television stations. The person has to do a bunch of these things. So this is the problem.
And unfortunately, the way science is covered in the schools is only getting worse. And so people are getting a worse and worse background in science is what we know increases, and that's just going in the wrong direction, folks.
Yeah, so the health reporter is the one who's going to be... Oh, someone at my door. The health reporter is someone who's going to be reporting on a space news story. I will grab my door. I'll be back in 1 second. Go ahead, tell people more about the Hangout-a-thon.
Okay, so I have a link. It's conveniently bit.ly'd. If you go to lowercase CQ instead, it takes you to some Japanese site that I don't know if it's good, bad, weird, or other, because language I don't speak, not enough graphics. Anyways, capital CQ 2015 on bit.ly will take you to our donation link. I will update that link to point to the Hangout page once we have the Hangout page. We don't have the Hangout page yet. So our current plan is I'm in the process of doing the graphics and setting up the infrastructure. And once I have that, I'm going to be emailing out everyone who's joined us in major ways before and saying, look, we're doing something new this year. We're asking people not just to give money, which we need because otherwise I don't get paid. Quite honestly, you are the reason I'm paid currently. And beyond that, we want you to do science. So we're going to be asking for sponsors. Celestron's already come on board to donate door prizes for people who participate. And people who participate in doing science or in giving money are both eligible for the door prizes for participating in our Hangout-a-thon. If you are a small business, large business, artist, any of the above, and would like to get on board on helping drive people to participate in this, let me know. We're going to advertise as many of the door prizes, I need a better word, as many of those as I can ahead of time so that you know what's up. And I'm going to be working on filling in the schedule. It's something I'm actually kind of looking forward to because it's through these activities that I've gotten to know so many of you over the years, And that's been a really awesome experience. There have been moments of stupidity I will remember for the rest of my life, confusing the words prosciutto and the one that's the sparkling wine and the one that's the thinly sliced pork. I've confused those two words and merged them into one word on air, and one of them you don't toast with at the end of 36 hours. Anyways, yes, that's the pork, and Prosecco is the drink, which I really like. I like both of them, but one more than others to celebrate. So we're hoping that you'll all come running into it. I'm going to start doing more and more live mapping over the internet so that you can tune in and map along with me. But again, I need to first set up this infrastructure, but the link is going to be CQ 2015, capital C, capital Q, otherwise you end up on a weird Japanese, well, I don't know if it's weird, you end up on a Japanese site.
Okay, this question comes from, this is I think the time for the last one. So this question comes from Randall from Calgary, Alberta, and Randall wants to know, so well, here's the gist. The Terminator, right, is this line that demarcates between daytime and nighttime on the Earth. And since the Terminator is moving essentially at the speed that the Earth is rotating at about 1,000 kilometers an hour, why don't we see, say we're in a big, flat, wide open place, why don't we see the Terminator rushing towards us at 1,000 kilometers per hour? Why does we just get night?
Atmosphere.
So care to expand upon that?
I love it when there's a one-word answer. But put more expansively is as sunlight hits the atmosphere, which is really thick, the atmosphere diffuses light, scatters it, Rayleigh scattering, and it's that scattered light that we continue to see illuminating us once the actual sun has sank below the horizon.
Right. So there's just, if we were on the moon and standing,
totally.
Standing on a mountain and then watching the plane, we would see the Terminator move across the lunar plane. But in our case, because there's so much scattering, we just can't. It's just everything just fades, and then it's dark time. It's dead time.
So do not watch Star Trek 3. Skip it. Go from 2 straight to 4. Leonard Nimoy, we love you. Star Trek 3 was a mistake. There's a scene where they're on Vulcan and the Terminator rushes over everyone, and I'm like, but then you were dead because there's no atmosphere.
And then you had to die. Yeah.
Yes.
Michael Jobin says, will there be stickers?
Huh?
I'm assuming for the Hangout-a-thon?
I'll make stickers if you want stickers.
Yeah, we made some stickers. I'm going to find the sticker. 1 second. Hold on.
Drop me an email to remind me. My brain is a sieve. starstrider@gmail.com. And I've lost Fraser while he goes foraging for stickers.
And maybe this is what Michael's talking about. So we made, for the Guide to Space.
Oh, is that for your Patreon campaign?
Yeah, so we made for our patrons, for a bunch of our patrons this year, this is our mission patch for 2015. And so I'm not saying we're going to make mission patches every year, but we made one for this year. So if we do that, I'm going to have folks come sit in my house throughout the Hangout-a-thon, mailing them in real time, because otherwise it will never get done. Nancy Graziano, I may be sending you an email. Or Susie, yeah. Susie organized our this whole campaign, so it was really fun. Cool. All right, well, why don't we wrap things up? So thanks, everyone, for watching. Don't forget to help share information on CosmoQuest. There's Pamela's link, bit.ly, CQ 2015. And we'll see you all next week. Oh, next thing happening, what? Have you got anything on Wednesday?
Yes. Wednesday we have the Inspiring Science Education Hangout. Come join me. I'm going to be talking with the principal investigator of Herschel about how we understand star and planet formation and introducing a new lesson for those of you who are K through 12 educators. Stay for the second half. Those of you who aren't, only stay for the first half. Introducing a new lesson plan on how to get modern-day star and planet formation into the classroom.
Cool. And then, of course, we've got the Weekly Space Hangout on Friday with a special guest this week. So stick around. All right. We'll see everyone next week.
Sounds good, Fraser. I'll talk to you later.